All right, this is our last section of new material from the textbook. Did you realize that? It's going to take us a couple days to cover it. But today we're going to take a look at measures of central tendency, and we will start the part that's called variation. So there are three measures of central tendency that we're going to talk about. And the first one is the one that is most familiar to you. It is called the mean. The mean, also sometimes called the arithmetic mean, is the quote-unquote average of the values. It's typically what you mean when you use the word average, where you take all of the things that you're adding them together and you divide by a total number of something. So this is how we calculate your average in the class, right? We take the total number of points that you've accumulated, we add them together, and we divide by the total number of points that were possible. If all the assignments were weighted equally, we could actually divide by the total number of assignments there were instead of the total number of points to figure out what the average assignment value was. But this is what you are typically meaning when you say the word average. You're meaning a mean. It is not the only way to determine the central tendency of a data set, though. So imagine for a moment that you had A's on everything, but they were like really close to the borderline A's. Maybe this has happened to you. And all of a sudden you tank an assignment that's pretty significant, enough that it lowers your grade down to a B. Well, you might be able to say, but wait, I got A's on everything but this one thing. That's not an accurate reflection of my, material that I've learned in the class. And you might be right? So this is not always the way that people think of as a good way of determining an average value. Another type of an average is called the median. The median is the middle value that is found by listing all the numbers in numerical order. Logistically, if there are an odd number of values, there will be one value that's in the middle. If there are an even number of values, there will be two numbers that we would consider to be in the middle. And when that happens, we would find the mean of those two numbers. So picture teacher salaries for a moment. If you talked about the average salary of an employee at a specific, like an educational certified somebody at a school. Okay, so I'm not including, like the custodial staff or those kind of positions, but the full-time people, teachers, administrators, and so forth. And you took the average. It might be that if you threw the superintendent's salary in there, it makes it look a little funny. Right? Because the superintendent or the principal or whoever is that highest paid person might have so much larger of a value that it makes it skewed. It makes it look like the average salary is really higher than what seems reasonable for teaching staff, for example. So whenever you have an outlier, an extreme value, either high value or low value, like for instance, if you were in this class or another class where you were taking tests and there was one test that you just missed and you have a 0 on it, or something like that, it is going to astronomically affect your grade. It's going to drastically change it. But that doesn't really measure your level of understanding of the material, and perhaps it would make more sense to talk about what happens if you left that value out somehow. There are arguments like that going on right now in education. How do we approach this idea of zeros, these really low values, tanking grades, when maybe levels of understanding should indicate a higher level of understanding? These are topics of question. So a median value would simply take the middle value of all the values instead of taking the average by adding them together and dividing by the number of values. Okay? The same thing could happen if you were talking about somebody's heights, right? Like, so if we had everybody's height in here and then we threw in here, Shaquille O'Neal comes in it. That doesn't make sense to average him into the heights of the people in the room, right? It would drastically enough change the average that it would somehow feel disingenuous, right? So having these extreme high or extreme low values get affected, the mean will get affected, whereas the median is just almost unaffected at all. And then the third way of doing an average is a mode. The mode is the number or numbers that occur most frequently. So when you imagine like a clothing manufacturer trying to decide how many of different sizes of clothing that they want to make, well, they're trying to figure out, not the average person, right? We don't want to add all the people's, clothing sizes together and make a whole bunch of that particular clothing size. They're somehow trying to figure out what the most people want, right? Mm-hmm. What is the most prevalent size that they need to make in order to accommodate the people who will come and will want this particular shirt, pants, hat, whatever you got going on. So a mode might be an appropriate measure of central tendency in a situation like that. So what we're going to do next is we're just going to practice finding these three quantities given a couple different data sets. Okay? So here's our first data set. It's very small because I just want us to practice the computational process of it. We have, I think there's 7 numbers here. And we're going to find the mean, the median, and the mode. So the first one, mean, what do? Add the values. Yeah, add the values together. You can do one of two things for me. You can either write out that you intend to do that, 18 plus 22 plus 22 plus 17 plus 30 plus 18 plus 12, add them all, and divide by 7. So if you want to show me that much work and then just spit me out an answer, that's fine. Or if you want to show me not necessarily the numerator that's there, but the sum that you got from your calculator as a step instead of this first step, that'd be okay too. What is the sum on the top? I don't have this one written down. I have the average written down, but not this. 139. Okay. And there's 7 on bottom, so this is almost 20. And we will go with 1 decimal as we're working on means, medians, modes, and the other pieces we're about to encounter later. 19.9. So either show me the first one where I've got all the numbers written out, or show me the second one where you've got the summation value over 7. One of those two show me, and you're 19.9. Okay, easy enough?
Does it matter what decimal you take it to?
That's what I was just saying. We're always going to take it to 1.
Okay.
Yeah, if the directions specifically tell you something different, follow the directions. But if not otherwise indicated, just go with 1 decimal, and we'll be good with that. Yep. Okay, so that's mean. Median. So to do median, what do I need them? How do I need them to be written?
Numerical.
Yeah, I need them in a numerical order. And you could go smallest to largest or largest to smallest. It really doesn't matter. I think our natural tendency is to go smallest to largest. So that's what I'll do. I have 12, 17, 18, 18, 22, 22, and 30. And I have an odd number of values here, right? So there actually is a middle value. Which one is my middle value? 18. Which 18?
The second one.
Yeah, the second one. This one is the one that's occurring in the middle. So my median, I almost said mean, my median is 18, the middle value. And there's no context on this problem. We'll see problems later that have context where we would write units with it and so forth, but there's not anything on here. Mode. What is mode? Number or numbers, could be, that occurs most frequently. So what number or numbers occur the most frequently? 18 and 22. It is possible that all the numbers would occur once, or maybe all the numbers occurred twice. If you had a situation where every number occurred exactly the same number of times, there is considered to be no mode. Okay? If you have 2 modes, this would be considered bimodal, and we would have trimodal and so forth. Cor?
So for the mode, we don't have to show what your work.
There's nothing to show. Yeah. Nope, there's not. In fact, your median work is probably the nicest place to see the mode because they're putting them side by side, right, so to count from there. But yeah, there's really nothing to show for mode. Yep. Okay, you ready to look at another one? You might have done something like this in your past. I know I did once upon a time too. The mean score on a test of 20 tests is 75. What is the sum of the 20 test scores? So not something directly like this, but have you done something where you said, I have this average and Canvas is not working to show me if I put this number in, will I get an A in the course? And I wanted to know if I could do it by hand. You know what I'm talking about? You know that feature in Canvas where you can play with your average and figure out what if I get this on the, I think it's called what if. Does it say what if? Yeah, what if scores. Yeah, so the what if inside of Canvas is doing an algorithm that's based on what we're doing right now. That's what it's actually doing. And it's not hard to do it by hand to actually figure out these values as well. This one's just asking us to find a sum. And so if you come to my office and you actually wanted to find out a value you need to do, this is what I tend to do to show you how you calculate your values. So this one has a mean score of 20 tests. You wouldn't have 20, you'd have like 4 in a class, right? But you have 20 tests as 75. What is the sum of the 20 test scores? Well, mean is found by taking the total, in this case the total of points, and dividing it by the number, in this case the number of tests. How many do I have? So I know the mean, it's 75, and I know the number of tests, it's 20. So what I don't know is the total, or the sum. I actually think I'll write the word sum here. That's a little bit more descriptive than the word total. Let's write sum. So how can I find this?
Multiply both sides by 20.
Right. I would just multiply both sides by 20. If the average score is a 75 and there's 20 scores, then the sum should be 75 times 20. What is that? 1,500. This one does have context, so we would write points. This is 1,500 points. Okay. So my knowledge of football is rather limited, but I can do the next problem okay with a little bit of like descriptive phrases, so we're going to look at that together. We have linesmen and backfield. Those are the descriptors here. So if the mean weight of 7 linesmen on a team is 230 pounds, and the mean weight of the 4 backfield members is 190 pounds, what is the mean weight of the 11-person team? All right, so this is actually an extension of the last problem that we did. Okay, so we do not know the total weight of any of these particular players. We know an average when you put them in sort of these groupings, right? That's much like over here. We know the average of the 20 test scores in this grouping. Well, in the grouping of the 7 linesmen, we know their average weight. And in the grouping of the 4 backfield members, we know their average weight. So we can actually find each of those pieces as well. So we can find the mean of the first group is going to be the sum over the number of them. So these are our linesmen. This is the line. And then I've got the backfield, so I'll label them back. I've got their mean, and it's their sum. In this case, it's the sum of the weights, not a sum of the points, sum over the number of them. And then I'll show you, this isn't the only thing we have to do, but this is the starting point that looks just like the last problem. What's the mean of the linesman?
230.
And how many of them are there? 7. What's the mean of the backfield? 190. And how many of them are there? 4. So it would not make sense to simply add the 230, the 190, and divide by 2, because they represent a different number of people. One of them is 7 people and the other one is 4 people, right? So we can't just add the 2 weights and divide it in half because I don't have equal numbers of people in these groups. But I can do like I did on the last one, and I could take the 7 times 230 for the first sum. And I can take the 4 times the 190 of the second sum. And this would be the total weight of the football team if I add these together. So what is 7 times 230? How much? 1610. So we're going to use that in a moment. And what about the 4 times 190? 760. So what I really want is I really want the average weight of the entire football team. How do I do that? Well, it's the same thing. It's the mean equals the sum divided by the number. But my sum this time is the sum of the total weights, which is the 1610 plus the 760. And what is my total number? 11. So go ahead and add those together and then divide by 11. Sorry, 215.5 what? Pounds. Make sense? Now, do you have to do it in all these 3 separate steps? No, you could compile all the steps together and, can merge some of these pieces together, but the process is still the same. I need to figure out the total weight of one group, the total weight of the other group, and I need to figure out when I add those together and divide by the total number of people from both groups combined, what do I get? And I would have 215 pounds. Now, it should make sense that the number is between 190 and 230, doesn't it? Well, it should be, right? It shouldn't be more or less than either of those values. That wouldn't make sense, right? Also, it should make sense that it's tending more toward this weight that was the 7 people, right? I'm closer to the 7 people's weight than the 4 people's weight because there's 7 of them there that are dominating the value. So those things, just as a quick looking back and say, does it make sense, is a good idea to do. Okay, we're about to shift gears. This is measures of central tendency. We're done. Now we're going to look at measures of variation. Ready? Lots of measures of variation. First one, range. Range is used in lots of mathematical contexts. It's used in other contexts as well. What we mean in terms of statistics when we say range is simply the largest value minus the smallest value. Okay, that's the range of values. Right, like if I were to tell you the range of the age of children, my oldest is 24, my youngest is 9. She had a birthday last week. You guys missed it. She would have been excited for me to tell you Friday was her birthday. I would take 24 minus 9, and that subtracted value, which is 15, would be the range. My children range by 15 years in age. From my youngest to my oldest is a 15-year age range. Okay, that's range. These others are interesting. The lower, middle, and upper quartile. So the lower quartile is the value below which 1/4 of the data lies. 25% of the values lie below that. The middle quartile, which is also the median, they're equivalent, the middle quartile is the median, is the value below which 1/2 of the data values lie. And the upper quartile is the 75% mark. It's the value below which 3/4 or 75% of our data lie. So thinking about that perspective, I'll come back to my screen in a sec, but this median being 18, it's my Q2, right, the middle quartile. Do you see that half of the values, namely right here, lie below the mean and half lie above the mean, and we have this weird 18 itself, which is in the middle, that we get excluded from. We don't talk about him. We just talk about the values excluding him when we look at median. So half of the values are below, the other half of the values that are not him are above him. That's marking the 50% mark. So imagine that these were weights of dogs. I think we could probably do that. You can have a 12-pound dog and a 30-pound dog, no problem. Context matters. I can't tell you these are grades. That would be sad. No grades. Let's do dogs. Dog weights. And you had 7 of you brought your dogs, and these were the weights of the 7 dogs. I could say that the 18-pound dog is the median weight. Half the dogs weigh less than 18 pounds. The other half weigh more than 18 pounds. Make sense? That's what this would mean. And it would be the same thing when I'm looking at the other quartiles. I can talk about 1/4 of the dogs being below a certain point, or I can talk about 1/4 of the dogs being above a certain point, or 3/4 being below equivalently. And that's looking at the upper and the lower quartiles. We're going to actually use this data set, the one that I flipped back to in a moment, and find that upper and lower quartile as well. All right, our next one is called the interquartile range. The interquartile range is just the range between the 25% mark and the 75% mark. How much space is between those? So if I were to do that in my house, I would find the child's age, who's the 25% mark, and I would find the child whose age, who's the 75% mark, and I would subtract their ages. With my dog weights, I do the same thing. Within a given data set, the lowest or smallest value is called the lower extreme, and the largest or highest value is called the upper extreme. Should make sense. And a box plot, also sometimes called a box and whisker plot, can be created using much of the details we just described. The lower quartile, the median, and the upper quartile, the interquartile range, and the upper and the lower extremes. So it's a way of drawing the information out where you can see all those pieces. You lose the specificity of the exact values, but you can see these sort of important data points still on the graph. Okay, so that same data set that I mentioned before, we're going to use it again. Once upon a time, in the first couple slides, we put them in order, so let's put them in order again. Okay, and we had already marked this 18 value as our median. We're going to call it Q2 now since we've got a letter for it. So we ignore it because it's already been associated with something, and we only look at the values before it. So we have 3 values before it. When I'm looking for Q1, I'm finding the median of the first values that are excluding the rest. So now that I'm finding the Q1, I'm looking only at 12, 17, and 18. What is the median of those 3 values? 17. So 17 is Q1. And I do the same thing for my upper values. What is the middle value there? Q2, or 22 is Q3.
What do you do if there's 4 instead of there being 3?
Yeah, so I mentioned it, but I didn't show you an example. So since you've asked, let me show you an example. Let's say that at the beginning there had been a 10, 12, 17, 18, and we wanted to find the middle of that. What we do is we need something that's sort of in between 12 and 17, right? So we find their mean. We do 12 plus 17 divided by 2. So on this one, is it 15 and a half? I think it's 15 and a half would be the median of those values. And then if I was wanting to find, like, splitting it again, like I would do, I just don't exclude anything because I didn't have either of the values here. So then I would look at these 2 and these 2. So like even though it would be weird, we could do the Q1, Q2, Q3 with even just 4 data points. It would be possible to do. It would be weird. It's not enough data to really give you any valuable information, but you could do it, like mathematically speaking. Does that help? Okay. So let's draw, a couple other things. We need a lower extreme and an upper extreme. If we've put them in order, it's very nice to see. The 12 is my lower extreme, just because it's the smallest, and the 30 is my upper extreme. It is the largest. All right, so let's talk about how we draw this on a box plot. So you're going to draw a number line. The number line, we're not going to actually be on it. It's just giving us a scale, okay? Most times we do that. That's not the case. But this is a scaling number line. And you're going to mark the lower extreme value. So we will call that 12. And we've got to do hash marks until we get to the upper extreme value that we have, which is 30. So make sure that your hash marks look like they're approximately evenly distributed. You don't want something looking like really wonky like this, right? Like that's not 12, 13, 14. That doesn't work. We would need something in between. So this would be 13. You don't necessarily have to label all of them. Just like on some of our other axes, I tend to label in increments. 2s sometimes, it might be 5s if the data set's big enough. Whatever makes sense to you, but you want to label at least some of them to give you some perspective. Might be spreading this out a bit much. No, I think I'm okay. All right, a bit much. Let's just shift it over. $12 to $30. So what we're going to do is we're going to make dots for the 5 important values that we've marked. The lower extreme, the upper extreme, the Q1, Q3, Q2, Q3. And we're going to make them sort of not parallel, but like collinear. They're going to be all on the same line. So it's going to look something like this, not on the line that I just plotted, but there's going to be dots here. So I'm going to dot at 12. I need a dot at 17. I need a dot at 18. I need one at 22. And then I need one over here at 30. Okay. Those are just a reference point for us. The dots on the outer extremes, like the lower extreme and the upper extreme, those really stay dots. The other ones actually are going to become vertical line segments. They're going to look just like this. Approximately equal in height if you can try to make them so. And then you're going to connect them with a box in the middle, like this. And then those dots that you originally plotted that were on par with the lower extreme and the upper extreme get drawn out to the edges. Mine's not perfect, but it's not too bad. And you can see why it would also sometimes be called a box and whisker plot. Those outer pieces are often thought of as whiskers on the plot. So what is useful about this? Well, at a glance, I can tell some things. At a glance, I can tell where the median is. At a glance, I can see the range. I can see how high the graph goes and how low the graph goes, right? I can also see where the 75 and 25% marks are. 75% of the data is below 22. 25% of the data is below 17. I can see a lot of general information about the grouping of the data, but I've lost a lot of the specificity, right? The only specific values I really know that exist are the lower extreme and the upper extreme. Everything else could be actually averaging, like the question Laura asked, what if it's an even number, right? Those dots that I put for Q1, Q2, Q3 might not even represent data values that I have, but they divide the data values into pieces at the very least. You would need a title for this. So let's just, for a moment, imagine we've got the dog situation that I had before with the weights of the dogs, so that we can put a title on this, and then we can talk about what these values actually mean. So let's say, for instance, that the context is these are all weights of dogs. So our title would actually be just that. These are the weights of a group of dogs. Okay. We could actually talk about the fact that 50% of the weights are below 18, right? 18 pounds. So 50% of the dogs weigh less than 18 pounds. We could talk about the fact that 25% of the dogs weigh more than 22 pounds, right? Or that 75% weigh less than 22 pounds, if you prefer. We could talk about the fact that the lowest weight dog that's present is 12 pounds, or that the highest weight dog present is 30. All those pieces would apply to those descriptions of our information. Is that all right? All right, so this is a box or box whisker plot. The next one that we're going to look at, and this will be our last one for today, is called mean absolute deviation, and I will abbreviate it MAD. Okay? So this makes use of the absolute value to find the difference that each data value or each data point is away from the mean. It's found by taking all absolute value differences and averaging them together. The process by which we do this is easier to do than to say. That happens sometimes when I'm giving a description about stuff in mathematics. There's another one that's in between here that says variance, standard deviation. But we're going to jump to the example at the bottom of the page, which is finding this mean absolute deviation that this is describing. Okay? So example 5 at the bottom of the page gives us the same data set that you're now loving. You love this data set. You know it very well. Okay? You can keep it in the order it's given. You can change it into the order that we had it from smallest to greatest. It doesn't matter in the slightest what you do. But we found early on, in like the second slide that we did together, that the mean, which the mean is actually written with a bar on the top of it like this, X bar, that's the notation for mean, is 19.9. We did that earlier. So I'm dragging that in from before. Everybody good? All right, what we're going to do is we're going to create a table, not because it's absolutely the only way to do it, but because it's a pretty nice way to do it, and it will extend into what we do next time with standard deviation really well. So the first column is just going to be all the X values All right, the data values that I have, and I'm going to leave them in the order that I'm given them. So it's 18, 22, 22, 17, 30, 18, and 12. And then the next column takes those scores, that's the X value, and it subtracts off the mean, that's X bar 19.9, and it takes the absolute value. You might feel like, well, that's kind of a lot of steps. But the reality is, it's just trying to find out how far away from the mean you are, and it doesn't care whether it's positive or negative distance. That's all that's saying. So for example, 18, how far do you have to go from 18 to get to 19.9? 1.9. And I don't care about if it's positive or negative, it's just 1.9 away. How about 22? How far away do you have to go from 22 to get back down to 19.9? 2.1. And I have another one of those, so I'll write it twice, 2.1. How about 17? How far away are you if you're at 17? 2.9. How about 30?
10.1.
Okay, is everybody tracking on what you're thinking about? You can legit follow the formula if you want. Like, that's fine. If you want to actually put them every time in, you can. But you can also conceptualize the difference on this one because the numbers are kind of small. 18 we already did, so that's another 1.9. How about 12? 7.9. And all the mean absolute deviation does is add these together and divide by 7 because there's 7 values. So if you add these together, what do you get? Grab a calculator. You probably don't want to do that in your head. $28.9. And if you divide by 7, what will you have? 4.1. So this is saying that the average distance that the values individually are away from the mean, or that the mean are away from your individual values, is about 4. Right? It's about 4 away from your values that you were given. So what we'll do next time is we'll jump back up to the part we just skipped with these pieces about deviation, and we'll do another calculation with this particular problem, and we'll pick back up there next time.